Okay, so we've just finished talking about functions of two variables and looking at regions bounded between the graph of a function of two variables, say f of xy, and here's the graph of our function, something like this, and it sort of lives above a region in the xy plane, and this double integral we've been talking about gives the volume of this region. Where this integral is taken over this region R in the xy plane, and we sort of break it up into small little rectangular prisms and add up all of those individual values to give us the total volume. So we have a nice geometric way to think about double integrals, is finding volumes underneath the surface that is the graph of a function of two variables. So we want to extend the idea to triple integrals and functions of three variables. Now, unfortunately, there's not going to be a nice geometric way to think about what the resulting kind of numerical quantity is when we do a triple integral over a function of three variables. It's really going to be almost like a four-dimensional volume. But we can still define it. So let's take a function of three variables, x, y, and z. For now, we'll just assume that it's greater than or equal to 0. And what we can do is, first of all, we can say that this function is continuous on a closed and bounded region R, but this closed and bounded region is going to be some subset of three-dimensional space. And so our go-to example will be some sort of like rectangular box in space. So this is going to be like the domain of our function of three variables, R. So here's our region R. Okay, so it's a three-dimensional box. Okay, so maybe the x coordinates here can go from, say, A to B. The y coordinates can go from, say, C to D. And then the z coordinates can go from maybe E to F, like that. So we can think about this box as being this product of these three intervals, AB, and then CD, and then EF in the Z direction. Okay, so what are we really doing? Well, what we're going to do is we're going to take a small little box region inside of here that we're going to call dV. Okay, so a small little piece of the volume. And then we're just going to take the value of the function there and multiply it by that volume. So we're just adding up the function values on each of these little pieces dV, and that's giving us our triple integral. So we'll denote this triple integral with three integral signs. So f of x, y, z, and then multiplied by dV. So you see all we're doing is we're just taking our little volume region and then multiplying by the function value. So maybe in this little box, the function represents the temperature. So that's a little piece of constant temperature. And we can add up all of the little pieces of temperature in the box to get the total temperature. Maybe to do something like find the average temperature or something like that, just to think of a physical application. And so we can solve these triple integrals by doing iterated integrals, just as we did for double integrals. So In this case, when we have kind of a rectangular box region, we have a version of Fubini's theorem that says we can basically integrate in any order we want. So we can kind of fix an x-coordinate. So if we fix an x-coordinate, then we can look at our y-coordinate changing like that, and then look at all of these going along the z and get sort of a plane of values like this, and then integrate for all x values back and forth. I know that's a little bit hard to visualize, but first here we're fixing an x value between a and b, then y is going to go from c to d, and then z is going to go from e to f, and that's going to cover the whole region. Okay. And then we just want to make sure to preserve the order. So first here we're doing dz, and then we're doing dy, and then we're doing dx. And again, we just want to work from the inside out. So for the innermost integral, we want to treat x and y as if they're constant, find an antiderivative with respect to z, and then move out. This new function will be a function of y and x. We'll treat x as a constant for the second integral, find an antiderivative with respect to y, and then finally we'll integrate that last function as a function of x. So that's the idea. We're basically just breaking up volume regions in R3 into little pieces, multiplying by the value of the function there, and then adding up all those values. And just like with double integrals, we can do it in an iterated way. First z, first y, then x, or really in any order we want most of the time. Okay, so we saw how to deal with rectangular regions, and that's kind of the simplest case. But in general, a region in space, so a three-dimensional region, we can think of, most of the time, as sort of being, so maybe two functions of z, of x and y, so maybe we have our first function of x and y, and here's kind of the plot of this surface. And then maybe we have a second function. So a second curve that's like f2 of xy. So these are two surfaces. And then what we can think about is kind of the volume formed between them. So most regions we're looking at can actually be thought of in this way. Somehow they're being bounded between two functions of z, like this. And so if we look down into the xy plane, so here's x, and here's y, and here's z. So if we look down, we can think about, okay, this volume region, we'll call it R. It's bounded between these two surfaces. We can also think about it as living above some region, some area region in the xy plane, like this. So here's our volume region in between these two surfaces. But somehow z, for any fixed x and y in this region, so if I fix a point x and y, then z is going to go from, well, f2 of xy up to f1 of xy, like that. So z is varying between these two functions, like that, for any xy. And then our x and y is varying over this region here. So, we can do the same sort of thing we did for functions of two variables. Once I think about z changing from f2 of xy to f1 of xy, well, then I can think about, okay, well, maybe I fix two y values, say a and b, and then maybe I can think about this region that's actually lying below my two functions as being, okay, this is some function of y for that fixed value of y between a and b, and maybe this is some function down here that's some other function of y, so g2 of y. And so there's a lot going on here, but this is basically what we're doing. So when we set up this iterated integral, what we're going to do on the very outermost integral, we're going to fix a y value between a and b. And then now for that fixed y value between a and b, x is going to vary between g2 of y and g1 of y. And this is going to describe the area region below the volume region I'm looking at. So I'm just thinking about all the various xy points that give me z values bounded between these two surfaces. And so for an xy pair kind of picked in this region, this was sort of the double integral idea, I have a z value that's going from f2 of xy up to f1 of xy, like that. And then we have, well, say our function that's defined in this region R. So f is again this continuous function defined on R. And that's the function that we're adding up the function values over this region, or integrating. And then we have dz. And then here we're adding up x values. And then we're picking a y value between a and b, like that. So this is just setting up an iterated integral for a region that's bounded between two functions of z. And sort of the projection onto the xy plane is an area region that's bounded between two functions of y, like that. And of course, you can imagine other regions, maybe that are bounded between two functions of x and z, or y and z, or anything. And most regions are going to be able to be described this way. Okay, so the last thing we want to do is just talk about a couple simple applications of triple integrals. So the first thing we can do is say we have a closed and bounded region R. Well, we can actually find the volume of this region similarly to how we found the area of a region for functions of two variables. We just integrated the function 1. Well, that's exactly what we're going to do here. So if we can describe the region sort of in terms of our limits of integration, then all we need to do is just integrate the function 1 and then add up all of the little pieces. And this is really just going to take, sort of break up the region into small pieces, add them all up, add up all those volume regions, and that's going to give me the total volume. And then we can also think about, once we have the volume of a region, the average value of a function of three variables over a region R. And again, we'll denote this by kind of f hat or f bar, kind of like that. And it's going to be, well, the triple integral of f over this region. So that's going to add up all of the values. And then we're going to divide by the volume of the region, which of course we'll do by computing this triple integral in this way. So this has a lot of really nice applications. things like center of mass, or I think I already mentioned that, if f is a temperature function, well, you can add up all of the temperatures over a volume and you can find an average temperature in a room where maybe the temperature is different in different locations, things like that. You can also, I think I mentioned center of mass. Anytime you have a function defined over a space region, maybe it's an electric field, electric potential, you can find sort of the average value. And it's a really useful application of the triple integral. All right, so here's our first triple integral that we're going to evaluate. And so notice a couple of things first. So this is an iterated integral, so we're going to do the first integral first, which is an integral with respect to x. And notice that the limits are functions of y and z, which are the outer variables of integration. And then the second integral is just the limits are just functions of z, which is the outermost integral. And so when we go to find this integral, we want to treat y and z as constant within the first integral. So we have 0 to 1, 0 to z, and then we take an antiderivative with respect to x, and we get 6x yz, evaluated from 0 to y plus z. Okay, and then we have dy dz. And of course, we're evaluating this function as a function of x. So this is going to be the integral from 0 to 1, integral of 0 to z, and then we just evaluate x at y plus c. All right, so now our new function is just a function of y and z. And this is just a typical double integral. So we sort of have reduced the triple integral down to a double integral. And next we'll reduce the double integral down to a single integral. And that's sort of the way this goes. Okay, so what do we do here? Well, we find an antiderivative here with respect to y, treating z as a constant. So let's do that. So let's do some scratch work here. So this inner function is 6y squared z plus 6yz squared. And we're first taking an antiderivative with respect to y. So we have antiderivative here is going to be 2y cubed z. And then plus, here we'll have 3y squared z squared, evaluated from 0 to z. Okay, so let's plug in z. Plugging in 0 will make everything 0. And so we have 2, this is going to be z to the 4th, plus 3z to the 4th. So we have 5z to the 4th. And then this is a walk in the park. We just take an antiderivative with respect to z, but that's z to the 5th over 5. So we just have z to the 5th, evaluated from 0 to 1, and look at the final answer. Just 1. Simple as it comes. So this crazy triple integral evaluates simply to the number 1. All right, so here we have a triple integral of this function over this region R that's defined here. And it's not always going to be easy to visualize the regions, but it's worthwhile to at least attempt, because it's going to help you see sort of what's going on. And the more you practice trying to visualize, the easier these will become, and the more you'll learn to trust yourself to kind of say, okay, well, there are two functions of z here, and then sort of what's going on in the xy plane, etc. So let's just kind of naively try to sketch this region. So now this region is just bounded by a bunch of planes. so let's draw our three-dimensional coordinate system. Here's x, here's y, and here's z. Okay, so let's look at these planes. So we have x is equal to 0. Well, that's the yz plane. Then we have the plane x is equal to y. So here's, well, the line x equals y. And then we kind of have this plane going off like that. Okay. So this is the plane x equals y, like that. And we've already had the plane x equals 0. So that's just this yz plane. Now these planes are going to intersect along the z-axis, like that. Okay, so here's the plane x equals 0. Okay, and then we have the planes y equals 0 and y equals 1. So the plane y equals 0 is going to be just the xz plane. So this is y equals 0. And it's going to intersect, all these planes are going to intersect on the z-axis. And then we have the plane y is equal to 1, which is going to be parallel to this plane, like that. And this is actually going to cross this plane at y equals 1, like that. And I understand this is already getting extremely complicated to see. Okay, but the point is, so this is just all going on in kind of the xy plane, more or less. So this really complicated thing going on in 3 dimensions, what I want to do is I want to actually sketch kind of the projection down onto the xy plane. Because this is a mess. And I mean, it's okay if you sort of have gotten lost in this picture. So let's plot what's going on here. So recall that we had the plane x equals 0. So that's going to be just going along the y-axis right here. Okay, and then we have y equals x, like this. Okay, and then we have y equals 0, which is the x-axis. And then we have y equals 1, which is going to be up here. Okay, so the bounded part of the region in this plane is right here. So what that means is that for any given x and y, x and y is going to live inside this triangle. So x and y. And then for any x and y in that little triangle, well, I didn't actually draw the plane z equals y and z equals 2y, but you can imagine that z equals y is going to cut through this way, and then z equals 2y is going to cut through with a slightly bigger slope. So in other words, z equals y is going to be on bottom, and then z equals 2y is going to be on top. So in other words, if we look at sort of the innermost integral, then z is going to go from y to 2y. And that's going to be for any fixed xy in this little bounded triangle right here. Okay, so let's think about what's actually going on in this triangle. So for a fixed x and y in this triangle, z is going to go from y all the way up to 2y. So it's going to be like this plane and then this plane up here. that I'm not drawing, because it's just going to make this picture even more convoluted. Okay, so let's say that I fix a y value between, this is 0 and 1. Then notice that x, for that fixed y value, is going to go from 0 all the way to y. Like that. And of course, I've fixed a y value between 0 and 1. Okay, so the function we're integrating is xz sine of y to the fifth. And then we first did z for a fixed x and y. And then for a fixed y between 0 and 1, we looked at x and then, of course, y. So this is the setup for this triple integral. And it's really important if you can just remember, most of these regions can be described as bounded between two functions of z for x and y in some region in the xy plane. So that's kind of the pattern of a lot of these problems. Okay, so how do we actually evaluate this integral? Well, we take this function here, we think about it as a function of c with x and y constant, and we find an antiderivative. So this is 0 to 1, 0 to y, and then we get x z squared over 2, and then sine y to the fifth, evaluated from y to 2y. And then we have dx and dy. And so we'll have 0 to 1, 0 to y, and then we have x times, okay, so we have, this is going to be 4y squared over 2, so 2y squared, and then minus y squared over 2. When I evaluate at y, and then we still have sine of y to the fifth. And then this will be dx dy. Okay, so next I take an antiderivative with respect to x. Well, this is the only thing that involves x. So I have the integral from 0 to 1 of x squared over 2 evaluated from 0 to y times this function of y, which is 2y squared. Well, let's actually combine. So 2y squared minus y squared over 2 is 3y squared over 2. And then sine y to the fifth dy. And of course, if I evaluate x squared over 2 from 0 to y, I'm just going to get, well, y squared over 2. So what do we have? We have a 1/2 and a 3/2, so we can factor out actually a 3/4 from the integral, or from the integrand. And then all we're left with is y squared times y squared, which is y to the fourth, and then times sine of y to the fifth dy. And if you remember your Calc 2, this is a classic u substitution problem. So we want to let u be y to the fifth, then du is 5y to the fourth dy, or we'll have a du over 5 is y to the fourth dy. And so we can change our y limits. They're still just going from 0 to 1. Because when y is 0, u is 0. And when y is 1, u is 1. And so we factor out this 5. So what is our constant? So we have a 3/5, but then we also pick up a factor of 1/5. So that's going to be 3 over 20 integral from u equals 0 to u equals 1. And then we have sine of u du. Like that. Okay? All right, so then let's just evaluate an antiderivative. So we have 3 over 20, so an antiderivative is going to be cosine of u, 3 over 20, cosine of u, and we're actually going to pick up a negative sign because an antiderivative is going to be negative cosine, and then evaluate it from 0 to 1, or in other words, we get negative 3 over 20 times, well, cosine of 0 is 1, and then cosine of u, or cosine of 1 is just cosine of 1, minus 1. Okay, and this is the answer. And notice that this actually is a positive number because cosine of 1 is going to be smaller than 1. So this will be a negative number times negative 3 over 20. So as we expect, we're getting a positive value when we do our integral. Okay, so we want to find the volume of the region bounded by these surfaces. And so here we just want to set up the triple integral and integrate the function 1. But the key is to set up the triple integral with the limits correctly. And what we want to notice here is that this region is bounded between two functions of x and y, or two curves in the z direction. So z is 0, that's just the xy plane, and z is 1 minus y. So the region is bounded between two functions of x and y. So we can think about for a fixed x and y in some area region that we'll describe in a second, z is really going from 0 to 1 minus y. And then we'll just have our function 1 and dz. So now let's think about what values of x and y we're fixing to allow z to vary between 0 and 1 minus y. So let's look at the xy plane and see what bounded region we're working in, what bounded area region that is. So first of all, recall that the xy plane is the plane z equals 0. So if z is equal to 0, notice that this equation here reduces, if I set z to be 0, to y equals 1. In other words, that's the intersection of the plane 1 minus y with the xy plane. And so let's look here. We have x equals 0, y equals root x, and y equals 1. Here is x is equal to 0. Here's y is equal to 1. And here's y equals root x. And so the region we're working with for a fixed x and y is this region right here. Okay, so let's say we fix an x value. Okay, so definitely the left bound will be 0. And notice that if this line is y is equal to 1, and this curve is y equals root x, they'll meet at x equals 1. So we can fix an x value between 0 and 1, and then look at where y is going to go. Y is going to start for a fixed x value between 0 and 1. We're going to start at square root of x and go up to y equals 1. So for a fixed x between 0 and 1, y is going from root x to 1. So for a fixed x and y, z is going from 0 to 1 minus y, kind of above this region. And then where's that x and y fixed? Well, for a fixed x between 0 and 1, y goes from root x to 1, and then x is going from 0 to 1. So that's the idea. You just kind of want to work your way out, starting with z, and then here's y, and then x. So we've set up the iterated integral that's going to give me the volume of this bounded region. So now it's just a matter of solving it. Well, the innermost integral is where I want to start, and that's a walk in the park. Okay, so an antiderivative of 1 is just c, and then I just evaluate it 1 minus y. When I evaluate it 0, I of course get 0. So I'll have 0 to 1 root x to 1 of just 1 minus y dy dx. So I've reduced this down to a double integral. Now let's reduce it down to a single integral. So I take an antiderivative of 1 minus y with respect to y. And so I'll get y minus y squared over 2. And that's evaluated from root x to 1. Okay, so let's evaluate that. So if I plug in 1, I'm going to have 1 minus a half. So that's 1/2. Then if I plug in root x, I'll get minus root x, and then minus x over 2. So plus x over 2. All right, and now we finally reduced it down to just a single integral. So let's take our antiderivative with respect to x. So we'll get x over 2. This is really x to the 1/2, so that'll be like 2/3 x to the 3/2. And then plus, this will be x squared over 4. And all of this is evaluated from 0 to 1. When I plug in 0, I'll get 0. So I just plug in 1 for x, and I get 1/2 minus 2/3 plus 1/4. So let's practice our fraction addition. So this is really, looks like we're going to have to use 12. So this is 6 over 12 minus 8 over 12 plus 3 over 12. But that's just 6 minus 8 plus 3, that's 1. So 1 over 12 is our final answer. That's the volume of this region bounded by these surfaces. Okay, so we want to integrate this function, x times y, over this region, the tetrahedron with these vertices. And so I'm going to try to plot this tetrahedron just so you can see it. And like I've said before, it's worthwhile if you can try to sketch some of these regions just to sort of begin to visualize what's going on. So the vertices of this tetrahedron are here. So if I put 1 and 2 on all of my axes, okay, so I can plot the point 1, 1, 1 right here. And then I can plot 1, 2, 1 right there. And then 2, 1, 1 right here. And then 1, 1, 2 right here. Okay, so this is this tetrahedron. So it's sort of like a pyramid. It has 4 sides. And the key thing we want to see here is that these 4 sides are given by 4 planes in space. One of the planes, notice that these 3 points here, the x-coordinate is all equal to 1. So one of the planes is x equals 1. Because 3 points that are not in the same line will determine a unique plane. I also have 3 points where the y-coordinate is 1. So y equals 1 is another plane. That's going to be this side plane here. So this is x equals 1, the back plane, y equals 1, the side plane. We also have z is equal to 1, which is going to be the bottom plane, because these 3 points have z coordinate equal to 1. And for the 4th plane, the plane that's kind of lying on its edge right here, I'm just going to make a clever observation and notice that these 3 points here, if I add x plus y plus z, I'm going to get 4. So this is the plane x plus y plus z equals 4. Or in other words, z is equal to 4 minus x minus y, like that. Okay, so we have 1, 2, 3, and 4 planes that this tetrahedron is bounded between. Okay, so notice that for any fixed x and y point in this lower triangle, well, z is going to go from 1 to 4 minus x minus y. It's going to go from the bottom plane, which is z equals 1, up to 4 minus x minus y. Okay, and then we'll integrate the function xy dz. Now we just need to see, okay, well, where am I fixing an xy point on this triangle so that z goes from 1 to 4 minus x minus y? Well, the intersection here that's going to give you my x and y points are in the plane z equals 1. So if z is equal to 1, then notice that, so z is equal to 1, then I can plug in 1 here, and I get y is equal to, well, move some things around, 3 minus x, okay? And then x is going from 1 up to where y is 1. Well, when y is 1, x is 2. So x is going from 1 to 2. So y is going to be going from 1 to 3 minus x. So that's here, 1 to 3 minus x, like that. And then x goes from 1 to 2. So this is the setup for the iterated integral over this tetrahedron region. All right, so now we're ready to just actually integrate this function. So the inner integral, I just want to take an antiderivative with respect to z. So this inner integral here. Okay, so now that I have this triple integral set up, I'm actually just going to plug it into a computer algebra system at this point because it gets a little bit messy. But what we see is that the final answer is 31 divided by 120. And that's the integral of this function xy over this tetrahedral region that we have described here.